Thank you.
Yeah, little bits of chaos all around. Has anybody made a Friday the 13th joke yet?
I was trying not to think about it because it was already like acting like Friday the 13th before I even left work this morning. And I was like, whenever I saw Eric's message about Wagman about like 50, 60 mile per hour winds up north, I said, oh, this is going to be a great day. So
All right. Well, the good news, I mean, there's definitely terrible news that our guest speaker for today couldn't make it, but she is going to be presenting in April. So if you were really eagerly waiting to learn about Betelgeuse and its companion star or theoretical companion star, you can get to hear that presentation on April 10th. I've got a few backup presentations that I've given to other clubs over time, and this is one of them that I've given both to the Roanoke Valley Astronomical Society down in Virginia, but also to the overall Astronomical League. And I picked this one because hopefully it's a good one if the Astronomical League wanted it. As Kristen mentioned, I'm having some internet problems as well because I'm on hotel Wi-Fi that hasn't been wonderfully stable for my entire trip, but we'll see how it goes. Through this presentation. There's only, I think, one slide that has a little bit of animation associated with it. So this is a presentation that I gave back 4 years ago or so, whenever we had just launched the James Webb Space Telescope out to Lagrange point L2, which you can see on the image that's on the title slide here. And well, why did we put James Webb all the way out there? What even is a Lagrange point? And that's the basic theme that was encompassing this talk is why are we doing this with James Webb, and what exactly is a Lagrange point? So let's start off by not talking about either of those and start off by talking about Hubble. So the Hubble Space Telescope is definitely one of the signature things that NASA has done over the past 36 years. It launched in 1990, and over the past 36 years, well, after it got a pair of glasses, because there was some issues with the mirror grinding, a little bit of inaccuracy. So maybe for the last 33 years, it's made some iconic images and some really impressive scientific discoveries. You know, if I can get the animation to go from here, there we go. Things like the pillars of creation in the Eagle Nebula, just a completely famous picture that is a Hubble product. Whenever Shoemaker-Levy 9 impacted Jupiter, we had Hubble ready to go to take pictures of those impacts in the southern hemisphere. The Hubble Deep Field, looking at a point of sky a little less than the size of the full moon that appeared to be pretty empty, and seeing thousands upon thousands upon thousands of galaxies. Discoveries like the first direct image of an exoplanet around Fomalhaut is just another thing that Hubble has done. But Hubble, well, it has its issues and it has its challenges. You know, it had to be repaired 4 different times through space shuttle visits, and the reason that we were able to do so is because it's in pretty low Earth orbit. You know, you typically think of low Earth orbit as about where the International Space Station is, 200, 300, 400 miles up. Hubble is a little bit higher than that, but it's still within 1,000 miles of Earth. It's something that still constitutes low Earth orbit. And so we're able to send astronauts out to do some repairs over time to replace the gyroscopes that keep it pointed in the right place, to update the instruments to new technology that wasn't available whenever it first launched, and to fix technology that was there when it first launched, but was not working quite properly or maybe broke down over time. I mentioned the idea that Hubble needed a pair of glasses, and it was a great thing that we were able to send up a team of astronauts on the space shuttle at the time to be able to correct for the little bit of distortion that was happening in the images, like this image of M100, the original wide field camera, the left image from 1993. Definitely looks blurry and unimpressive compared to what happened after we added some corrections into the light path and also added some corrections in to some of the optical processing. And I'm talking about Hubble in particular, and the fact that Hubble is nice and close that we can repair it in particular, because we're not going to be able to do that with James Webb. And part of the reason that we're not going to be able to do that with James Webb is because James Webb is primarily an infrared telescope. It does have a little bit of light gathering power in the visible light spectrum and a little bit in the UV spectrum, if I'm remembering right. But the bulk of the collection that it's able to do through its imagery is in the infrared. And if we put it really close to Earth, well, believe it or not, Earth is warm. We all live in a place where Earth is generally warm, maybe the present winter discounted. But whenever the Earth is receiving energy from the sun, it's going to take that energy in and it's going to radiate it out in the infrared. And if we're picking a $10 billion telescope up in space, we don't want it to be blinded by something really, really warm, less than 1,000 kilometers away. And so we had to move it to somewhere else. We had to put it in a place that is a little bit further away from Earth, but still someplace where we can easily communicate with it. We know that it's going to be in a fairly stable orbit over time. And the place that we chose is one of two. And so where is the James Webb Space Telescope? So here's a NASA image production, kind of a general timeline for what's going on in the James Webb mission. All of this has luckily been successful, as we've all seen with James Webb pictures that have come in over time. But the sort of orange, sorry, not orange. Why? My brain is not able to talk in words tonight. This gray circle, let's pick the right color, is the orbit of the moon. And you can see the orbit of the Earth around the sun in green. We're sending something well past the moon out further and further and further into space until we get to this ring that's circling this text labeled L2. It takes about 14 days for the spacecraft to get out there. It was about 30 days overall for the spacecraft to get into the right orbit and be operational. But this location, L2, it's about 900,000 miles from Earth, and compare that to the orbit of the moon that's 240,000 or so away from Earth. We're talking about something that is 4 times further away from the Earth than the moon is. And so we probably should have a pretty good rationale for putting a telescope all the way out there. The representation that I've got here on the slide definitely shows that in kilometers instead of miles, but same basic idea, right? Hubble is orbiting at something like 570 kilometers up. James Webb is going to be 1.5 million kilometers away. It is 1.5 million kilometers away compared to the 384,000 for the moon. Here's another comparison that you can think about. Take the general size of a quarter that you're used to holding. If you put the overall scale of the Earth down to the size of a quarter, then Hubble is going to be orbiting about a 1/20th of an inch above the top of the quarter, where the quarter is less than an inch across overall. So it's very, very close into that quarter. The moon, if anybody wants to take a guess how far out that's going to be relative to the size of the quarter, feel free to shout it out or put it in the chat. I'll pause for a couple of seconds to take a drink of a Red Bull. 2.4 feet. It's 2.4 feet away from that quarter to get to the moon. And well, we already see the scale for James Webb a little bit further up. James Webb is going to be much, much further out than that. It's going to be almost 10 feet away. It's going to be 9.3 feet away from that quarter. So it's definitely out there. It's definitely out in the solar system away from the Earth. But again, we probably need to have some good rationale for why we're putting James Webb, why we're putting this $10 billion space telescope all the way out there. Again, another representation showing that from the sun to the Earth, it's about 150 million kilometers. We've got the orbit of the moon shown orbiting around the Earth, and then 1.5 million kilometers further out than that, we've got the little cross and the label L2. What exactly is this L2? Why is this L2 point so important overall? There we go. Arrows that point to L2, just in case you missed it. So that brings us to the main point of the presentation, which is what is a Lagrange point? The L in that L2 stands for Lagrange, but what exactly is a Lagrange point and why were they named the way that they are? So first off, just the terminology note, there are a number of different places that use different terminology to associate with Lagrange points. I found in the research for this presentation, some places saying Lagrangian point instead of Lagrange point, some places just saying L points, which is a nice abbreviation for the L1, L2, and so on points. Also, libration points is another term, but I'm going to try to stick with Lagrange points. Just know that if you're reading some of this literature on your own, you might find some other terminology that still means the same thing. So all of those are equivalent, and here is a representation of the 5 different Lagrange points. So they are numbered L1 through L5. L1 is in between the Earth and the Sun. L2 is on the other side of the Earth from the Sun. L3 is on the other side of the Sun from the Earth. if that's not a confusing enough way of saying it. And then L4 and L5 are just kind of off at a weird angle. Not actually a weird angle, it's a 60-degree angle, which is important for equilateral triangle purposes. We got something that is on an angle that is putting it about as far away from the Earth as it is putting it away from the sun. Another thing that is kind of key and important to talk about is that this is not something that is completely limited to just the Earth-Sun system. And so if we're talking about replacing the Earth in this image with Mercury and also deleting the moon because Mercury doesn't have a moon, there's going to be an L1 point for the Sun-Mercury system. And there's going to be an L2 point for the Sun-Jupiter system. And there's going to be an L3 point for the Sun-Eris system and an L4 point for the Sun-Uranus system and so on. You get the general idea. This is not something that is unique to the sun and the Earth. And it's not even just unique to the sun being at the central point, because there's going to be an L1 point for the Earth and the moon. There's going to be an L2 point for the Earth and the moon, and so on. These are just labels for locations in the solar system that are, well, it turns out, nice and gravitationally balanced between the two main masses that we're talking about. In this case, the sun and the Earth, but it could be the sun and any other solar system object, basically, or again, the Earth and the moon, Jupiter and one of its Galilean moons, and so on. They all have these Lagrange points, although with the Galilean moons, they can be a little bit interfered with by other Galilean moons. Maybe a little bit more on that in discussion a little bit later. But here is a more complex representation trying to show almost in a topographic map form what these gravity wells look like. So there's a gravity well in the sun, there's a gravity well around the Earth, and that L1 point is just at the right point to be at balance within that saddle point where the gravitational balance of the sun and the Earth meet. And it turns out that if you extrapolate that even further, there's a nice saddle point gravitationally at L2 where the Earth and the sun's gravitation balance out, and at L3 and at L4 and at L5, where L4 and L5 are a little bit more like regions that are stable rather than individual points that are stable. And it also turns out that those L4 and L5 points, you know, they're more semi-stable than they are actually stable. They are places where the items that might be orbiting the sun in those locations, orbiting the whatever central point in those locations, just kind of drift around a little bit instead of being in a specific location. Here's one more that's a nice little 3D representation showing, again, L1, L2, L3, L4, and L5, and maybe doing a little bit of a better job of showing that L4 and L5 are off at those 60-degree angles between the Sun-Earth system. Another thing that you might see is that the L3 point almost looks like it's a little bit outside of the circle. And that's not a feature of the image here. That's actually true. It's going to be a point that is not exactly on the opposite side of the sun from the Earth, but just a little bit further out from the sun than the Earth is in this representation to get to L3. Here's another one that is wrong because L3 is closer to the sun than the Earth. And there's a lot of weird information on the internet trying to figure out exactly where this L3 point is supposed to be portrayed. I'm here to give you the final definitive ruling that L3 is actually supposed to be a little bit further out from Earth's orbit on the other side of the sun and not inward from Earth's orbit on the other side of the sun. Okay, so Lagrange points. Here is the paper in its original Latin that originally described the first three of the Lagrange points. So again, the three that are kind of in that nice, neat line in the Earth-Moon system. One, or not the Earth-Moon system, but the Sun-Earth system. Again, though it doesn't really matter which of them is the two masses that we're talking about. But since we're talking about James Webb, let's stick with Sun and the Earth. So on the Sun-Earth system, there are these 3 points, L1, L2, and L3, and there are some of the equations that are showing where these points are. I'm not expecting you to look into it in a whole lot of detail because I'm going to talk about it in slightly less detail, but the two things that I want to call out on this paper in particular are going to be what the title of the paper is. It's about the rectilinear motion of 3 bodies attracting one another, which is something that we haven't really talked about exactly quite yet. We've talked about the sun, Earth, we've talked about the Earth, Moon, but there needs to be a third body in this scenario, and that's going to be the body that we're trying to position at one of these Lagrange points at L1, at L2, and L3. And so there's not just going to be 2 masses that we're worried about, but there's also going to be a third mass that we're worried about and trying to position that third mass about the first 2 masses. The other thing that I want to mention is the author of the paper. You might imagine that these things are called Lagrange points. It must be a guy named Lagrange who discovered these, but it's not Lagrange. It's a guy who you might be aware of if you're a fan of mathematics. It's a guy named Leonard Euler, who was one of the primary mathematicians of the early part of the 18th century. He was a guy who discovered lots and lots of different things in mathematics, and it turns out that he also discovered the first 3 Lagrange points. So just a little bit of a timeline between Leonard Euler and Joseph Louis Lagrange. So they had a little bit of overlap in time where they were both working at the Royal Prussian Academy of Sciences. It turned out that Euler actually recommended Lagrange as a person who was going to replace him at the Royal Prussian Academy of Sciences, because Euler wanted to go back off and work in St. Petersburg for a little while. But the overall timeline, Euler was born in 1707. In 1727, when he was 20, he got a job in St. Petersburg. That was probably a good idea at the time, given the political stability in Europe. Going off to Russia was a good thing at the time. He was pretty happy there for a good while, but after 14 years, he decided that it was time to get a little bit closer to home, and so he wanted to relocate to Berlin, and that's in 1741 when he went to the Royal Prussian Academy of Sciences. Lagrange was born a little bit later in 1736. He got his degrees. He was well, there's several names for it, actually, some of them in French and some of them in Italian. But he spent a lot of time early on at the Turin Academy of Sciences, but he was ambitious. He wanted to go to some place that was a little bit more exciting than Torino. And he knew that there were places like Berlin that were really famous for their mathematics. He wrote a couple of emails off to Euler trying to join him, giving him some samples of his papers, giving him some samples of his work. Euler said, "Hey, this guy is actually pretty impressive. I'm going to give him my job, and I'm going to go back to Russia to be happy over there a little bit longer." The year after he went back to Russia, back to the Imperial Russian Academy of Sciences, is the year that he published the L1 to L3 Lagrange points. And so this was in 1767. And you can see over in the other column in 1772, Lagrange saw some of this work. He thought it was really interesting. He saw the points that Euler picked out, and he discovered 2 more of those gravitationally balanced points and published L4 and L5 in 1772. So that's the timeline that we're looking at here. This is late 18th century that these points were discovered. It's just that the majority of them, 3 out of the 5, were discovered by Euler. They all just got the name of Lagrange because, well, maybe there's just too many other things that are already named after Euler. We don't need to name everything after Euler. We can give his name a little bit of a break and give credit to some other mathematicians as well. So here's an example of the paper that Lagrange put together whenever he was trying to describe those L4 and L5 points. And here's a couple of the different names. There's Joseph Louis Lagrange, there's Giuseppe Luigi, there's Giuseppe Luvigo de Lagrange, different names for whichever country he happened to be in at the time. So back around to the Lagrange points. This is the big focus. This is what we're talking about, regardless of who it was that discovered them, whether it was the great mathematician Euler or the slightly less great but still pretty impressive mathematician Lagrange. We want to figure out exactly where these points are, and maybe the easiest one to talk about to figure out exactly where it's located is going to be L1. There's going to be a bit of the math associated with it, but I'm not going to dig too terribly deeply into the math. Otherwise, you would turn off this presentation. The first thing to talk about, maybe before we dig into the math, is the idea of orbital speeds and orbital periods. So as you go further and further out from the sun, you from Mercury, you step from Venus, you step from Earth, moving further and further outward, the orbital velocity of you going around the sun is going to be increasingly fast going in toward the sun, increasingly slower, decreasingly slower as you move away from the sun. And as a result, that's also going to greatly increase the orbital period of whatever it is that is in orbit around the sun. So Mercury being the closest planet, it orbits the sun at almost 30 miles per second. It's got an orbital period of about 88 days. Venus, you step out a little bit further, you get down to 21.75 miles per second. Earth, you step out a little bit further than that, you've got 18.52 miles per second, and so on, extending further and further out through the solar system. But if you're having something that is a little bit closer to the sun than the Earth, if you have something that's a little bit further from the sun than the Earth, like the L1 and the L2 points, you might expect that that orbital velocity is going to be a little bit faster for something that's closer to the sun, something that's a little bit lower, a little bit smaller if you're further from the sun. But then we have to take in the Earth's gravitation into account. And so you can imagine something at the L1 point is trying to race a little bit ahead, trying to get further and further ahead of the Earth than the sun, but the Earth is grabbing on and it's pulling it back a little bit to keep it at the same orbital period as the Earth is. Or if we're talking about L2, the opposite case, you might expect that something that's going to be out at L2 is going to have a slower orbital velocity around the sun. It's going to have a greater orbital period around the sun. But then when we focus in the gravity of Earth as well, Earth is going to be dragging along, or to increase that orbital velocity so that it's something that's going to be orbiting at the same pace that the Earth points. And so we're trying to find those exact mathematical coordinates for where this thing is going to be that is either a little bit closer to the sun, but closer to the sun to a point where the Earth's gravity is just pulling it back enough, or something that is further away from the sun, but just further away from the sun enough that Earth is still able to drag it a little bit further ahead. Here are a couple of examples of things that are in kind of close orbit that are trying to show kind of a similar gravitational balance. The moons Prometheus and Pandora around Saturn's F ring, and you can see the ring in the kind of inner part of the ring almost pulled a little bit toward Prometheus, because Prometheus, orbiting a little bit faster than those ring particles, is pulling on those ring particles gravitationally and accelerating them a little bit. You can see a little bit of the distortion in the ring as a result, and Pandora is doing the opposite. Pandora is kind of pulling things backward because it's orbiting the Saturn a little bit slower than all of the ring particles, and it's interacting gravitationally with all of those ring particles. So we've got our tiny little spacecraft, and we've got the sun, and we've got the Earth. Spacecraft not to scale, Earth not to scale with the sun, just a nice, easy representation. Let's come back to some of the math that you might be remembering from a high school physics class or something along those lines. Newton's theory of gravitation. So Newton's theory of gravitation says we've got a couple of different masses. We're going to call the sun M1, we're going to call the Earth M2, and we're going to call this spacecraft that we're trying to put in between the Earth and the sun M3. And we've also got some distances. So we're going to use a capital R for the distance between the Earth and the sun. We're going to use a lowercase r for the distance between the Earth and this mass, this spacecraft that we're trying to balance out. And we have Newton's gravitational formula. And that gravitational formula says that we're going to have the gravitational constant, and we're going to multiply that by the two different masses that we care about in the pairing, in this case, the Earth and the spacecraft. And we want to divide that by the square of the radius, the square of that distance between the Earth and this spacecraft. So we're trying to find that amount of pull that the Earth is pulling on this satellite and we're going to want to balance that against what's getting pulled on that spacecraft from the sun. Again, we're trying to find that nice gravitational balance point, that saddle point between the sun and the Earth. And so we've got the same equation over here, but now our denominator is going to be that capital R minus the lowercase r, because the satellite's going to be a little bit closer to the sun than the Earth is, so the distance is a little bit smaller. The good news is the gravitational constant cancels out. That mass M3 of the satellite cancels out. So whenever we're trying to find that exact distance that we need to solve for where to put this satellite, the mass of the satellite doesn't make a difference at all. We just need to deal with the two masses of the main bodies, the mass of the sun, the mass of the Earth, and also those distances, the distance between the sun and the spacecraft, the distance between the Earth and the spacecraft. There's also a third factor that comes in a little bit, and that's going to be related to the orbital velocity of that spacecraft. But this is a term that we really don't need to worry about so much for this conceptual idea of where we're putting the spacecraft. Just know that there's some additional Coriolis force that's going to be involved because of the fact that everything is going to be in this rotating reference frame where the Earth is orbiting around the sun and the spacecraft is orbiting around the sun, and the spacecraft is trying to orbit around the sun a little bit faster than the Earth is. But what we eventually work our way down to is that a lot of math happens in between, and then we end up with this formula for our first Lagrange point. So that distance r that we want to put this spacecraft from the Earth is going to be equal to the capital R, the distance between the sun and the Earth, and then multiply that by the cube root of the mass of the Earth divided by 3 times the mass of the sun. That's it. That's how everything kind of solves all its way downward to figure out exactly where the L1 point is going to be. And the first thing that I really want to emphasize is that this lowercase r, the distance that we want to put this thing between the sun and the earth, is something that is completely dependent on the capital R, the distance between the earth and the sun. Okay, well, the problem here is that the distance between the Earth and the Sun is not constant. The distance between the Earth and the Sun changes by about 3.5 million miles between perihelion and aphelion. And it changes instantaneously because the Earth is constantly in its orbit, moving a little bit closer to the sun, moving a little bit further from the sun over the course of the year, which means that our distance that we would want to have a spacecraft from the Earth is also going to be completely changing regularly. It's going to be changing continuously because this gravitational balance point is going to be changing instantaneously along with the distance between the Earth and the sun. So this location that we keep talking about, something that is 900,000 miles away from the Earth, something that's 1.5 million kilometers away from the Earth, turns out that that's not exactly true. It's going to sometimes be 899,000 miles from the Earth, 898,000 miles from the Earth, 901,000 miles from the Earth, 902,000 miles from the Earth, just depending on that distance between the Earth and the sun at any given time. The solution that we have here, as is called out by the animation that I just popped up, but is kind of partially blocked by my Google Meet sharing, the equilibrium solution to the differential equations of motion, something, the circular restricted three-body problem. I got most of that at least, even though part of it's hidden by the Google pop-up. But the important piece to take away is that this is the circularly restricted three-body problem. This is if the Earth had a perfectly circular orbit, then we would have something that is that exact distance from the Earth that would be that gravitationally balanced point. But because we don't have a circular restriction, because the Earth is in an elliptical orbit, that distance, lowercase r, is going to be changing pretty regularly. If you wanted to see more of the math, there's a really great YouTube lecture by AK Lectures, and it's going to walk through basically everything that I just talked through, but also in a little bit more detail. And what it eventually works its way down to at the end is the thing that I just put inside of the red rectangle with slightly different notation, but that distance that we're going to have is going to be scaled to that third root of the mass of the Earth divided by 3 times the mass of the sun. So it all works out if you want to dig a little bit further into all of the math behind where this balance point comes out to be. So what about L2? Well, it turns out that L2 is something that's easy enough to solve for. We just need to change the denominator of the sun to spacecraft distance. That's now going to be r plus lowercase r because the spacecraft is going to be further away from the sun than the Earth is. But if we keep all of the other notation constant, the distance between the Earth and the sun, capital R, the distance between the spacecraft and the Earth, lowercase r, we're just going to end up with the same solution at the end of the day because that addition, that subtraction ends up canceling out as we work our way through all of the math, and we see that that distance r that we're going to care about, that distance between the Earth and the spacecraft, same idea. The distance between the Earth and L1 is the same as the distance between the Earth and L2. It's just a difference between, are we putting the spacecraft on the inner part of the Earth's orbit or on the outer part of the Earth's orbit? What about L3? So L3 is going to be a little bit different, and I'm going to speed through this a little bit more. L3, again, just as a reminder, is this point on the other side of the sun from the Earth at whatever point in its orbit Earth currently is. And I also mentioned it's a little bit further away from the sun than the Earth is because we're also correcting for the fact that Earth is pulling something in that direction. Earth is adding its gravity to the gravity of the sun, pulling in that direction. And so something that needs to be gravitationally balanced needs to be a little bit further out in orbit and trying to orbit the sun a little bit slower in order to get that balanced force from that little bit of Earth's gravity that's still projecting itself all the way over 186 million miles away on the other side of the sun. The other representation kind of showing that balance point, that kind of saddle point for why L3 actually exists where it does, just kind of showing that it's not exactly the same kind of saddle point that we saw with L1 and L2, but it's still a region of gravitational balance. Another representation of L3, the one that I said was correct, the one that's showing it a little bit further out in the orbit of the sun, the one that was incorrect, showing it a little bit inside. I already kind of spoiled the reveal of, well, which one is correct Is it a little bit further out or a little bit further in? Turns out that it's a little bit further out. And the actual solution that we come down to for where it is located around the Earth-Sun system works out to this weird fraction of 7/12 times the mass of the Earth divided by the mass of the Sun, but it still has that capital R term associated with it, showing that the distance that we're going to have between the Earth and that spacecraft is going to be dependent on the distance between the Earth and the Sun. As that distance between the Earth and the Sun changes, the distance between where the spacecraft is going to be and where the Earth is going to be is also going to need to change instantaneously as the orbit progresses. L4 and L5, again, just speeding through it a little bit. We still got the spacecraft. The spacecraft is orbiting around the Sun. We're trying to come up with this gravitational balance point between where the is and that spacecraft, where the Sun is and that spacecraft. And it turns out that the R and the lowercase r and the capital R are going to be exactly the same for wherever the exact location of the center of this gravitational region is going to be. And an interesting note, though, is that these are a little bit less gravitationally stable than the other L1, L2, and L3. And there's a restriction in the masses of the two main bodies that we need to care about. And it turns out that if you take the mass of the Sun and divide it by 25, we need the mass of the Earth to be less than that. If the mass of the Earth was greater than that, then this is a Lagrange point that doesn't exist. And the same thing is going to be true if we're looking at the M3 mass. If the M3 mass, if this spacecraft mass is going to be less than the mass of the Earth divided by 25, then this L4 or this L5 point turns out to not exist. And that's actually the case out in the solar system for the Pluto-Charon system, because the difference in mass between Pluto and Charon is about 1/8 instead of the 1/25 that we care about. And so the Pluto-Charon system actually has L1, L2, and L3 Lagrange points, but it does not have an L4 Lagrange point. It does not have an L5 Lagrange point because it fails that first balance between the mass of Charon and the mass of Pluto divided by 25. We just don't have those gravitationally stable points out there, just given the fact that Charon is so massive in comparison to Pluto itself. But ignoring Pluto and Charon, back to L2 and the James Webb Telescope. So now we've got our Earth, we've got our Sun, and we've got James Webb kind of sitting out there. So we're putting James Webb out at the L2 point, right? We're putting it exactly at the L2 point. Turns out that James Webb is not exactly at the L2 point. There are a variety of reasons that we wouldn't want to put James Webb exactly at the L2 point. What we're doing is we're putting it kind of close to the L2 point. And going back to the rationale for why, again, we've got that circular restricted three-body problem. If we're trying to put something in a location a little bit further out from the Earth, a little bit further out from the Sun than the Earth, then that distance needs to decrease sometimes. And if that distance needs to decrease sometimes, then the telescope is going to actually need to turn around and fire its thrusters, pushing it a little bit closer to the Earth. And that's going to be a problem because it's an infrared telescope. And we don't want to shine the Sun's light on that infrared telescope. Another challenge that I just kind of popped up is there's going to be the three-body problem issue. This is something where if we only had the Sun and the Earth and the James Webb Space Telescope in the entire solar system, we would have a three-body problem, but we don't have a three-body problem because sometimes we're going to have the Moon, and the Moon's going to be a little bit closer to the telescope than the Earth is, and the Moon's gravitation is going to be pulling on the telescope. But sometimes the Moon's going to be over here on the other side of the Earth, and it's going to be pulling on the telescope, but it's going to be pulling on the telescope a little bit more weakly. And sometimes the Moon's going to be over here, and it's going to be pulling the telescope a little bit further ahead in its orbit. And you can imagine the same thing's going to be true on the other side. It's going to be pulling the telescope a little bit back in its orbit because everything in the solar system is going to have gravitation. You know, we also have, for example, Jupiter sitting all the way over here in the bottom left corner. But depending on where Jupiter is in its orbit, it's also going to be pulling on the James Webb Space Telescope and changing its exact orbital position around a little bit. Saturn, if we've got Saturn all the way off the screen in this not to scale orbital representation, Saturn's also going to be pulling on James Webb. Venus is also going to be pulling on James Webb. All of these things are going to have gravitational interaction that make L2 an actual unstable point to really put anything. It's only a stable point for the Earth Sun system in isolation. And sometimes Venus is going to be on the other side of the sun and pulling on the spacecraft a little bit more weakly. So the big takeaway that I've already kind of pulled out is going to be that this exact position of L2 is going to change every instant. And it's going to change every instant, both because of that dependence on the distance between the Earth and the sun, but also even if we solve for exactly where that L2 position is going to be, if we're thinking about solar system scale gravitational stability, it's not even going to be a balance point exactly at that L2 position. Sometimes it's going to be a little bit in, sometimes it's going to be a little bit out, sometimes it's going to be a little bit forward, a little bit back, depending on where all of these other massive objects in the solar system are influencing their gravitational balance in this big, messy 60 body problem, depending on how far you want to scale things up and how many objects you want to count and try to find the minute pull that Triton has on the James Webb Space Telescope as it's orbiting around Neptune. So we've kind of disproven these Lagrange points. They are nice mathematical objects, but even if they're nice mathematical objects, they're not exactly the stable points that we want them to be to put a spacecraft. But they're still useful overall. Again, there's a reason that we put James Webb out there because they are these points that are still semi-stable. How semi-stable are they? Well, if we put a spacecraft exactly on L1 or exactly on L2, it would stay there for about 23 days before it started drifting away. And so that's nice if we had a 23-day mission, but we don't want to have, again, a $10 billion space telescope that's in its correct location for 23 days and then kind of start drifting away. We want it to be out there for 5 or 10 or 20 years, depending on the length of the mission. L3, it turns out, is much more stable overall, but it's stable more on the order of 150 years before anything that we would put there starts to drift off a little bit. L4 and L5, I haven't actually found any specific value that says exactly how stable they are. It's just a while. Something will exist there for a while before it starts to drift a little bit away from that point. And here's the one slide that has a little bit of animation, so hopefully this is kind of coming through. This is all of the Trojan asteroids that are co-orbiting the sun with Jupiter. You can see that Jupiter is kind of pulling away a little bit. Jupiter is in its elliptical orbit, moving away from the sun and then starting to move a little bit inward, pulling in toward the sun. And as a result of that changing location, that changing capital R between the sun and Jupiter, all of these asteroids are kind of swarming around this Lagrange point L4, kind of swarming around this Lagrange point L5 in this semi-stable orbit. Some of them eventually get ejected from these orbits. Some of them get captured in these orbits. Some of them get a little bit too close to Jupiter. Some of them get a little bit too far away from Jupiter. But you can see that the core area of this gravitational range is going to be right around those L4 and L5 Lagrange points over the course of Jupiter's orbit. What else? I have a picture of the Earth-Moon formation in here for some reason, and I'm trying to remember why I had this slide in the first place. Now I remember. So whenever the moon was forming, one of the most popular theories right now for how the moon formed is that we had this this body that we call Theia that impacted the Earth early on in the early days of the solar system. It kind of got mostly absorbed into the Earth, but a lot of other material scattered outward, and that eventually aggregated into the moon. Well, there are some people who are theorizing that early on in the solar system, it wasn't just Mercury, Venus, Earth, Mars, and Theia. There might have been 100 different objects that were in the early solar system that were planetary mass sized. Some of them got ejected because of the gravitational pull of the outer planets. Some of them got ejected because they collided and then they changed orbits and started flying all over the place. And some are theorizing that this object Theia that collided with the Earth is something that for a while might have existed at one of those L4 or L5 Lagrange points in a semi-stable balance between the Sun-Earth-Theia system. But again, we had that issue of the M2 to M3 relationship. If the mass of the Earth divided by 25 was greater than the mass of Theia, then that becomes an unstable Lagrange point, and maybe that's exactly why this other body was surviving for at least millions of years, solar system timescale, enough time to differentiate, enough time to be nice and round, but then eventually ending up colliding with the Earth and forming the moon. So the failure of that M3 to M2 relationship might be why the moon formed. That math that was discovered by Lagrange in 1772 might be why we have a moon. Okay, James Webb. I already kind of talked about this a little bit. The fact that James Webb is an infrared telescope, and we want to make sure that we're not interfering with our infrared measurements by having the Earth heating things up or the sun heating things up. And so, if you haven't looked at the structure of James Webb in a while, here's a reminder that it's got this really big tennis court-sized sun shield, and this sun shield exists to block out all of the infrared light from the Earth, all of the infrared light from the moon, all of the infrared light from the sun, so that the detector on the other side, on the what we're going to call the cold side of the spacecraft, is pretty close down toward as absolute zero as we can get. This was early on in the mission where we actually had access to the temperature data from a couple of different sensors on James Webb, and you can see that the temperature differential between the cold side of the telescope and the hot side of the telescope is pretty substantial. We're trying to get rid of that that heat that's coming from the inner solar system and using James Webb to target things on the other side of that field. And so just as a kind of repeat of what I was saying earlier about what the issue is with putting James Webb exactly at L2. We've got the hot side over here on the left. We've got the cold side over here on the right. And if we put James Webb at this semi-stable location and James Webb starts getting pulled by, let's say, Jupiter all the way out on the same side of the sun during a Jupiter opposition, then James Webb is going to get pulled a little bit closer to Jupiter, a little bit closer to Jupiter, a little bit closer to Jupiter. It's going to get far enough away from this L2 point that it's going to just completely drift away from the L2 point completely. And so as a result, it's going to need to turn around, it's going to need to fire its thrusters, and we've got a sad face up here because now the telescope itself is going to be facing the sun, it's going to be facing the Earth, and we've lost some observation time because we had to point the telescope toward the sun, toward these other heat sources. And so James Webb actually turns out to be a little bit closer to the Earth than L2 just for that specific reason, because we want the telescope to always be drifting a little bit back toward Earth so that whenever we fire the thrusters, we're firing the thrusters and increasing its orbit a little bit, pushing it a little bit closer to L2, but ideally not pushing it beyond L2 where it would start drifting further and further and further away beyond L2. So again, another representation showing this kind of saddle point. If we have something James Webb related over here on the left triangle, the left blue triangle, it's going to get pulled toward Earth, and there's no problem with firing its thrusters and pushing it a little bit back closer to L2. But if we have it in the right triangle, it's going to keep drifting further and further away from L2. And the only way that we can get it back to this nice gravitationally stable region is going to be to turn it around, fire its thrusters, and lose some observation time. We want to make sure that we're always pushing the telescope a little bit away from Earth, but not too far overall away from Earth. There are some other reasons why we wouldn't want to put James Webb exactly at L2, and one of them is going to be what happens if our telescope is solar powered, like James Webb is. So it turns out that the L2 point for where James Webb is never going to be in the Earth's umbra. The Earth's umbral shadow doesn't reach quite that far, but the penumbral shadow does reach that far. And so whenever the telescope is on the exact opposite side of the sun from the exact opposite side of the Earth from the sun, it's going to be getting less light than it would if the Earth wasn't in the way, if it was orbiting a little bit further up in this representation or a little bit further down in this representation, so that we would have the telescope getting full overall sunlight if it was a little bit out of that alignment. And so what James Webb actually does is it orbits around L2. And so you can see a couple of these different representations looking at the orbit of James Webb from a couple of different angles. Maybe the one in the bottom left is the easiest one to get an idea of exactly what's happening with James Webb's orbit. It's cycling around L2 in what are called halo and Lissajous orbits. If we're looking at it in the bottom right corner from this perspective that's kind of looking in on the Earth, imagining that the sun is directly behind the Earth, we can also see that it's orbiting a little bit further ahead of the Earth in its orbit, a little bit further behind, a little bit below, a little bit above, but it's not exactly in the L2 position. it is orbiting around the L2 position. And it turns out that all of the other space telescopes that we've got at the L2 location, which, spoiler, there's more than one, are also following these kind of similar orbits. We don't want all of the spacecraft to be in the exact same location at L2, otherwise we would have lots of spacecraft collisions. But if they're all orbiting around this kind of semi-stable location and occasionally firing their thrusters to maintain these orbits and maintain their positions near this L2 semi-stable point, then we're golden. We're not going to have satellite collisions. We're going to be able to get our satellites all of the solar power that they need because the Earth's not going to be in the way. And so we got this halo orbit, this Lissajous orbit that is orbiting around that semi-stable point. We're showing the gravitational balances again, but now also adding in that orbit of James Webb that is, depending on the representation that you're looking at, depending on the angle that you're looking at, it appears that it's getting a little bit further away, but it can come back because the slope of the orbit actually allows it to come back a little bit. It's complicated physics that actually goes a little bit beyond my knowledge, but obviously it works because, again, we're putting James Webb out there along with a bunch of other space telescopes. A couple of other notes. So L1 and L2 are popular. I mentioned that there are other spacecraft at L2. Turns out that we've also got a lot of spacecraft at L1. So let me animate in a bunch of them. SOHO, ACE, Discover, Wind at L1. Discover is one that I was familiar with already because it's nice full Earth pictures regularly that are, again, full Earth because we're able to see the entirety of the Earth because the spacecraft is in between the Earth and the sun. SOHO is a solar observer. ACE and Wind I wasn't all that familiar with before I started making this presentation. But then other spacecraft that are further out at L2, Gaia, at the time that I initially put this presentation together, was still an active mission, and Gaia was out mapping the stars of the Milky Way from L2. This Spectre RG spacecraft was also sitting out at L2. And how about some more? So there are things that were going to be planned to go out to L2 and planned to go out to L1. Future missions that have already been named, things like the LISA Pathfinder, the gravitational wave detector is going to be at L1. The Chinese were going to put the Chang'e 5 spacecraft out at L1 as an Earth and solar observer. We've got the Planck mission. We've got the WMAP mission that was renamed recently, that were all going to be things that were also going to be crowding out at L2. And there are also going to be some future missions that have not actually gotten pictures of them. So I'm putting in a nice futuristic spacecraft to represent all of these other missions that, like, at least whenever I put the presentation together, there weren't renderings of the spacecraft, but there are renderings of Athena and Ariel and WFIRST now. But there are a lot of there's a lot of popularity. There's a lot of attention to these L1 and L2 points because they are these nice gravitationally stable points solar system wide. So what else might we find there? What else might exist at all of these Lagrange points aside from spacecraft that we put there? Well, how about asteroids? We already talked about the fact that there are these green asteroids, the Trojans and the Greeks, that are just aggregately referred to as the Trojan asteroids that are co-orbiting with Jupiter. And there's also a third group that is all the way out at the Sun-Jupiter L3 point called the Hildas that are sort of co-orbiting the Sun with Jupiter. Well, it turns out that Jupiter is not the only object in the solar system that has Lagrange points, and it's not the only object in the solar system that has asteroids with Lagrange points. So as of at least 2022, here are the total number of asteroids that have been discovered at each of the Lagrange points for each of these planets. And the first thing that jumped out at me, aside from the fact that the Earth only has 2, is the fact that Saturn actually has 0. There are no asteroids that have been discovered so far that are co-orbiting the Sun along with Saturn at either the L4 or the L5 Lagrange points. And that actually turns out to be Jupiter's fault, because if you're getting 60 degrees ahead of Saturn in its orbit, if you're getting 60 degrees behind Saturn in its orbit, then Jupiter is actually going to have a greater gravitational impact on the Sun, Saturn, L4 and L5 points than Saturn itself would have. And so those have been cleared of debris. But aside from Saturn and Mercury, all of the other solar system objects, all of the other planets in the solar system have at least one co-orbiting asteroid that have been discovered at those locations. There was actually even a nice paper calling out this issue. Where are the Saturn Trojans? Because we haven't been able to find them, even though we found a ton of them at Jupiter and a bunch of them at Neptune and some of them at Mars and a few of them at the other planets. Well, it turns out that Jupiter's fault is what's keeping Saturn from having any Trojan asteroids. But Saturn has some interesting orbital relations within its moons. So two of the larger moons of Saturn that you may have seen through a telescope are Tethys and Dione. And it turns out that at the Saturn, Tethys, L4 and L5 points are some moons. And at the Saturn, Dione, L4 and L5 points are some moons. They're obviously much smaller moons. There are things like Polydeuces down here that have barely been imaged by Cassini, and Cassini's mission's been over for 8 years now, so will never be imaged by Cassini at anything more than a little bit of a blur. But moons like Helene and Telesto and Calypso are co-orbiting Saturn with these larger moons, just at the nice semi-stable gravitational points that allow them to do that over time. There are also these things called Kordylewski clouds that are basically at the Earth Moon L4 and L5 Lagrange points, basically big collections of dust, not zodiacal light dust, but a different kind of sort of similar to zodiacal light that you can see at specific times inside of the seasonal orbit of the Earth and the Moon and the Sun, getting the right angles as well on top of that. So if you're out looking for zodiacal light and you happen to see a zodiacal light pattern that looks a little bit weird, that might have an extra ray or two associated with it, maybe you're also spotting some of the Kordylewski clouds at L4 and L5. What are they good for? Well, just as a last kind of couple of notes for things that we can do with these Lagrange points in the future, you might be familiar with Arthur C. Clarke. He came up with, well, in addition to being a science fiction author, he came up with a lot of ideas about geostationary satellites and space elevators and things along those lines. And he also had the idea that, well, what if we've got some kind of spacecraft that's going to be out, orbiting around the Earth-Moon L2 point? If we have that, then we have the ability to talk to things that are on the backside of the moon. And well, it turns out that the Chinese have actually done that with one of the landers that they had that had landed on the far side of the moon. They had something that was not exactly at the orbiting around L2 location, but actually orbiting around the moon, but a sort of similar idea. Just as Clarke proposed a little bit earlier in time, we can make use of the L2 point around the Earth and the moon to handle some communication satellite responsibilities. And here's the Chang'e 4 mission that's showing sort of what was trying to happen with that satellite. What else? So there's this thing called the B612 Foundation that's trying to look for rocks that might come in and collide with Earth in the future, but specifically looking for rocks that are going to be a little bit tough to find, asteroids that might be coming in from the direction of the sun. And if we have things that are coming in from the direction of the sun, as we saw with like the Chelyabinsk meteor, it's going to be something that we might not even detect, or we might not be able to detect with very much warning. And so there's a proposal that, well, if we can't see things that are coming at us from close to a sun direction, what happens if we put a satellite at the L3 point of the Sun-Venus system that can look out in that direction and look for anything that might be incoming into the solar system that might be a potential Earth impactor from that direction. So a proposed spacecraft that could be something located on the other side of the sun that would require some additional communication relays to actually be able to talk to, because again, it's on the other side of the sun. So we would need some kind of relay, maybe at the Earth Sun L5 point that's going to enable us to chat with this telescope on the other side of the sun. Similar idea. What happens if we have a telescope that's all the way out on the Earth-Sun L3 Lagrange point, and maybe it's doing something like monitoring space weather, like some of the space solar satellites have been over time. So we lose contact with those satellites as they pass behind the sun. But if we put another satellite at the Sun-Earth L5 or the Sun-Earth L4 positions, then we would have the ability to communicate with those satellites as well. It's just that we haven't had the investment to start putting satellites out at L4 or L5 yet. Same thing might happen whenever the Mars is on the other side of the sun. We lose contact with the rovers. We lose contact with the orbiters orbiting around Mars. Whenever Mars is at the opposite side of the sun from the Earth for a couple of weeks, well, we would still be able to talk to those if we had some kind of spacecraft that was at the Sun Mars or the Sun Earth L4 or L5 point that could redirect some signals around the sun and give us the ability to contact things on Mars for the entirety of its orbit instead of just the vast majority of its orbit. Getting really, really speculative, going into the future, what happens if we start terraforming Mars? If we start terraforming Mars, one issue is going to be that the sun is going to continually strip away any kind of atmosphere that we start injecting into Mars, because Mars just has a weaker gravity overall. It's not going to be strong enough to retain any kind of atmosphere. And also Mars doesn't have the nice magnetic field like Earth has. So what if we put a spacecraft at L1 of the Sun-Mars system that can generate a strong enough magnetic field to protect Mars and give us the ability to have a workable, breathable atmosphere on Mars? This is definitely getting into more speculative ideas. And to go into super speculative ideas, there was a guy named Gerard O'Neill who came up with these ideas of putting gigantic human settlements at the L4 and L5 positions of the Earth-Moon system that could be things like giant ring worlds that give us the ability to live in space that is at a semi-stable point to still enable us to get to the Earth, to still enable us to get back to the moon if for whatever reason the workers at these stations need to go to the moon to do whatever job they've got. Again, very, very speculative and futuristic, but proposals that were made by science fiction authors and space enthusiasts over time. And the very last thing to point out is that whenever we've got something at one of these Lagrange points in the solar system, it's only going to take a little bit of a nudge to push something out of that position and start drifting it into the solar system. And if you give it just the right push, then we've got basically zero energy required trajectories to get between different locations in the solar system. This is called the interstellar transport network, or something really close to that. The idea that we have these nice gravitational balance points where we can put things and we can store materials for missions, and we can store things for astronauts who may be going between planets, and then just giving that set of supplies a little bit of a nudge. And over time, it would drift from the Earth-Sun Lagrange point to the Sun-Earth Lagrange point to the Sun-Mars Lagrange point, or to the Sun-Jupiter Lagrange point, and still have a cheap way of getting supplies to astronauts who may be going to other places in the solar system, or maybe refueling missions to satellites that are orbiting some of these other planets. Getting refueling missions to something like the HiRISE telescope that's orbiting Mars and has been orbiting Mars for close to 20 years, taking really great pictures, but is going to be running out of fuel someday, and could be benefited by a little bit of a propellant resupply. Or we could be thinking about times in the future whenever humans are actually going to be there and we need to start resupplying colonies around Neptune. We can just put things at the Lagrange point, give them a little bit of a shove, and over time they will drift between these different locations in the solar system and can be captured by Lagrange points in other locations in the solar system for easy refueling and resupply. So that was the talk that I put together 4 years ago and haven't looked at since. Hopefully it was coherent and reasonable, and I'm happy to take any questions about it.
Thank you, John. Good talk.
Awesome.
Hey, John.
Yes.
Some of the members of the club may remember a space exploration club in Pittsburgh years ago called the L5 Society. And they were going I guess the thinking behind this thing, the L5 Society, is they would have their final meeting at L5 when a O'Neill cylinder was put out there, something like that. So, and a quick question for you, John. One of the Webb mirror segments took a meteor hit, which seems so unlikely. Don't these Lagrange points become dirty with space debris naturally collecting there?
Yeah, I suppose they would, and that might be one reason why one of the mirrors took a hit so early, much earlier than was expected. I would say that L4 and L5, given that they're a little bit more stable over time, would be things that are collecting a lot of that dirt and rock and debris a little bit more than say L2 would, because L2 just has the more ephemeral stability. But even then, there definitely is going to be some gravitational balance point there that can cause those kinds of issues for sure.
Thanks.
Yeah, I can't say for sure that that's the exact cause of why James Webb already took a meteorite hit, but well, I guess the good news is that I haven't heard about any others over the last 4 years, so maybe it was just an early coincidence.
Thank you. Okay.
Anybody else? Should I throw it over to Kristen for the break? Is Kristen still online?
Yep, I'm still here.
Okay, awesome.
According to Wikipedia, there's been 5.
Oh, really? Wow.
Yeah, but I guess they just only talked about the first one.
Or was the first one maybe the most major, and then the other 4 were smaller hits?
Yeah, it doesn't say, because I know it was like bigger than they expected. It wasn't like a dust, but it doesn't say here how big they were.
It just seems so improbable all the way out there. You know, it's one thing to have meteor hits around the Earth's gravity field, but so
Yeah.
Okay, was there any more questions for John? Okay, all right, John, kudos to you for putting that presentation on like literally last second. I will say that takes a lot to, and you just flew through that like no problem, like never hesitated. You just needed one break to take a sip of your Red Bull and you were good to go. So kudos to you for sure. Oh, I see there's a hand up. Is there a question? I think Rick. You'll have to unmute your mic. It should be at the bottom of your screen.
Oh, can you hear me?
Yes,
Yes.
we can hear you.
There was a power outage here, so I missed part of the talk. Why were they named Lagrange if Euler discovered the first Lagrange points? Why were they named Lagrange?
That's a great question that I really never found an answer to, aside from the fact that Euler is lots of other things are named after Euler, so maybe give Lagrange a little bit of credit for discovering a couple of them.
Well,
Okay,
it seems
was
like
there-
it seems like Lagrange was extremely important in physics. So, okay, thank you.
Yeah, give him a little bit of credit, I guess, to have discovered 2 of them and to have followed on from some of Euler's work. You know, this isn't like the only discovery that Lagrange made, but it's definitely the most famous for him.
Okay. Was there anything else? All righty.
This may be a little off topic, but all this celestial mechanics, I was wondering if Jean Mias was still alive.
What was can you repeat the name again, John? I'm sorry. I don't know if everybody heard it.
John Mias.
Oh, John Mias.
Jean Mias. Yeah.
Okay, and you were asking if he was still alive?
Yeah. Very famous contemporary celestial mechanic guy.
Oh, okay. I'm sorry. Does anybody, can anybody answer John's question? I might be able to Google it.
It's two E's, right?
Yeah, Meeus.
We died in
First name
1861.
J-A-N-E, yeah. He died in,
1861.
no, he was a contemporary guy.
Jean Mius or Jean Mius
Oh, yeah.
is a Belgian meteorologist and amateur astronomer, and his Wikipedia page says that he's not dead yet, at least. Born 12th of December 1928, so he's getting up there, but apparently is still alive as far as Wikipedia is concerned.
I keep forgetting I can look this stuff up on my AI, but thank you.
It's definitely a good point. That's not a name that I've thought of very, very recently. I see that he's a co-author with Fred Espenak on some of the solar eclipse books, and Fred is unfortunately no longer with us.
John, in a future talk, could you explain to us what a near rectilinear halo orbit is?
I will give it a try.
Future talk.
I can't promise that it'll be math free.
It says that John Mius, I guess, is still alive. He's 97 years old.
Yeah.
Okay. All right. I was gonna say, I know the wind is still going a little bit crazy outside, so I don't want to delay too much, just in case, you know, some more people may lose power. So far, so good. Is everybody okay if we just go ahead and move on to the meeting, or do we need a few minutes?
I'm fine.
Okay. All right. So we'll go ahead and get started. So it is 8:36 p.m. on March 13th, Friday the 13th, 2026. And I'm going to go ahead and call this general business meeting of the Amateur Astronomers Association of Pittsburgh to order. So thank you, everybody, for joining tonight. And again, thank you, John, so much for last minute putting a very well presentation together. That's all I can say about it. It was very, very last minute, and thank you. All right, Rich Dolish, are you online? I'm sorry, I didn't even take a look to see the whole roster for tonight.
I saw him.
Is he on?
He might have lost power.
Well, he said he was on with his phone a little bit earlier, but
Yep.
Here I am. I couldn't find the mute button.
Oh, whoops. All right. Are you able to read the minutes from last meeting?
Yeah, I got him here.
Okay, sounds good. Fire away.
All right, meeting minutes from the 3AP General Business Meeting, February 13th, 2026, 7:30 p.m. Business portion called to order at 8:42 p.m. by President Kristen Crawford. Presentation for last month was the Messier Marathon, Astronomy's Accidental Extreme Sport by Mig Ponce from the Las Vegas Astronomical Society. The business meetings from the business minutes from the January general meeting were read by Recording Secretary Rich Dolish. Lish made the motion to approve the minutes as read, seconded by Eric Fisher. Motion was unanimously approved. John Holtz gave his upcoming events. Highlights include Crescent Moon on February 18th, very close to Mercury. Total lunar eclipse on March 3rd, which of course we didn't see. March 7th and 8th, Saturn passed within 1 degree of Venus. And then April 4th, there's a potential appearance of a recently discovered sun-grazing comet. For the officers' reports, President Kristen Crawford reported that total membership stands at 312 following the end of the grace period. And then we will be having an executive committee meeting for the first quarter very soon. John announced the speakers for April and March. Also that the presentation slots are now filled through September. No updates from recording secretary, no updates from corresponding secretary. Terry Mealy was not present, but provided a 2025 year-end report. 2025 income was $15,000. 2025 expenses, almost $67,000, primarily due to Wagman renovations. IT committee was not present. Joyce Osborne Fisher announced a 21 plus night program at the Moonshot Museum starting in March, with the first topic being women in space. No updates from the membership secretary. Kristen read the names of the 3 new members that had joined since the January meeting. Tom Pfeiffer made the motion to accept the new members. Joyce Osborne Fisher seconded the motion. Motion passed unanimously. Observatory updates. Eric Fisher reported the gate combination was changed. New number posted on the 3AP website. I wants to monitor the inside of the building during the upcoming thunderstorms to check for roof leaks. For Mingo, Brian Crawford reported that the gate code change is pending, has not changed yet. And Becky Nichols is currently lining up guest speakers for the 2026 Haddad Planetarium talks. Old new business, Rich Dawlish confirmed the Ed Middleman donation includes 3 8-inch SCTs, a 6-inch Dobsonian, and high-quality binoculars. The online store is up and open for business. 6 members are confirmed to represent the club at the Northeast Astronomy Forum in 2026. New postcards featuring the observatories are being printed for the event. A nominating committee chairperson and 2 members are needed for the upcoming April-May officer elections. Sign-up deadline for members wishing to march in the March 14th parade. St. Patrick's Day parade was March 1st, and the quaffing for March was scheduled on the 7th. Motion to adjourn made at 10:35 p.m. by Joyce Osborne Fisher and seconded by Rich Dawlish. Motion passed unanimously. Those are the minutes.
Okay, thank you, Rich. All right, are there any comments or revisions that need to be made to the meeting minutes from February 13th, 2026? Okay, all right, may I get a motion to accept the meeting minutes read by Rich Dawlish at tonight's meeting? Marcus, I've seen one hand up.
Yeah, that's the motion.
Okay, and then may I get a second motion to accept the meeting minutes? All right, I think I saw Sean Brown come up. All right, all those in favor, please thumbs up, say aye. Aye.
Aye.
Okay. All right, are there any objections? If there are objections, thumbs down or say no. All right, any abstains? All right, motion passes. Thank you very much. Tom, we did hear your you're accepting before, I'm just going to mute your mic because we can hear a lot of background. So just letting you know. Okay. All right. Thank you, everybody. So motion passed. All right. Look at that by John Holtz. So John, when he emailed me, he said that most likely he wasn't going to be able to attend tonight's meeting. Eric, I
Yes.
think if you're okay with it, I'm probably going to volunteer you, if that's okay.
Yep.
To
That's
go
fine.
over his slide. I'm going to go ahead and pull that up right now.
I
That
just need you
way-
to. I just need you to advance the slides as I talk. Okay.
Absolutely. All right. Give me 2 seconds.
Reading glasses.
All right. I'm getting there. All right. Are you ready, Mr. Fisher?
Yes.
Okay.
Okay.
All right. So here's the upcoming events. Can you see that, Eric?
I see the logo, but I've got my own version of the.
Oh, hold
slideshow.
on. It must have taken me out of sharing. I'm sorry.
Huh?
Here's on standby.
Yeah. Okay, I have to apologize. I'm going to do this kind of haphazardly because I only saw this presentation last night.
It's all good.
We got the equinox coming up. Anybody would know what the word equinox means? Equal nights. Remember that. Okay. Crescent moon from the Pleiades. The nice thing about the moon and the Pleiades at this time of the year, the Pleiades is low in the west, or they are low in the west. You get a crescent moon with earth shine. It's very three-dimensional, okay, as opposed to like a gibbous moon conjunction with the Pleiades. Beta Tauri, see if you can see that star. If you remember, that Beta Tauri, I think, is one of the horn stars of Taurus. An occultation of Kappa Geminorum. If you can imagine Gemini standing up, it's going to be a star. You got Castor and Pollux, and it's off to the left. Full moon, I get that. Full moon. I'm assuming it's a full moon on the 1st. Very funny. By the way, April 1 is the tentative launch date for Artemis 2. And Spica close to the moon with unaided eyes. That's tough to do. And of course, it was mentioned earlier, we've got this comet maps. So we can go to the next slide. Well, maybe there might be a few more things here. Next slide. Excuse me again for jumping through haphazardly. Next slide, please. Hello. Oh yeah, comet maps. Last night was the first time I'd heard about it. Okay, maps is not an acronym. You usually have Atlas and Linear. This stands for Alain Maury, Georges Attard, Daniel Parot, and Florian Signoret. I thought comets only got three namesakes, not 4, whatever. So it's the initials of the 4 co-discoverers. And I've learned about something called a Kreutz sun grazer. I've never heard of this before. Apparently, any comet that gets near the sun close enough is considered a Kreutz comet, Kreutz. So as you know, comets are totally unpredictable. The medium's going to jump on this and say we're going to have the comet of the century. Does anybody remember Kohoutek or maybe Comet Ison? So it depends on the number of volatiles and on the comet if it's going to develop a big tail. So anyway, next slide, please. Oh yeah, by the way, only 1.2 solar radii. That's getting close. I'm surprised it wouldn't evaporate. Next slide. So John here is speculating that the Great Comet of 1843 was a Kreutz comet. And next slide, 1882. He's claiming this is a photograph. I thought the daguerreotypes, well, this is about the time of the daguerreotype photos, so maybe so. I think this is just an artist's touch-up. Next slide. Keiseki, I saw this one. It was a beauty. And I think another Kreutz comet. And what's the next one we're going to see? Next slide. Lovejoy. Yeah, that one I didn't see. Anybody else see Lovejoy? That was apparently another sun grazer. This common maps, it all depends on what proportion of it is, again, rock versus volatiles. All right. And we move on to the next slide.
I was going to say, Eric, was this so with it saying the C-2011, is that whenever we saw it, the 2011, or am I getting that wrong?
I don't remember seeing this comet. Maybe one of our more skilled observers saw it.
I think it was
Remember the
primarily
name,
a southern
Roger.
hemisphere object.
Say again, please.
I think it was primarily in the southern hemisphere that it was visible.
Okay. If you look real carefully, you can see the dust tail versus the ion tail, which is always kind of neat. Okay, and let's.
Yeah, I was gonna say, like, is it splitting? Like, that's what I'm kind of seeing, or is it just? It looks like it's splitting almost. It's kind of
no,
weird.
It can. A comet can fracture, and the coma is where it fractures. But this one, I think, is a dust tail and ion tail, but I might be wrong. Okay. So he's saying here that you can watch the comet transit the sun through a SOHO image. I guess so. But 1.23 solar radii, that's getting pretty cookie. So next slide. Oh, of course, now he's saying that this comet is going to be more favorable for the southern hemisphere. But if it really lights up, we might have a situation where the nucleus is below the horizon, but the tail's above the horizon, if it really lights up and evaporates. Throw in comments, by the way, while I'm going through these, if you want to. Okay. Nice diagrams. Go ahead. Photo section. Before we go past this one, something about Broca's cluster, okay? The Gaia spacecraft discovered that these stars are all moving in different directions. This is not a cluster. It's not a loose cluster. Read up on Gaia. What they discovered was amazing. Anyway, and this is one of the few objects that has 4 names. You've got Broca's cluster and the coat hanger, and I forget what the third one began with the letter C. Colander or something or other. And of course, the NGC number. So this thing has 4 identifiers, this grouping. Next slide. By the way, it's Aaron Zeitler. Here's a nice shot. Cocoon Nebula by Aaron. Aaron, I'm not sure if he's here tonight, but just pretty pictures. By the way, if you're not on Discord, go join Discord. You're going to see many pictures like this posted by our members. I think this picture was taken by Brian Crawford. Yes, there's his signature there. Astro in focus. By the way, Abell refers to a guy named George Abell. He was a famous astronomer, I think, at Palomar, who did a lot of deep sky work. In fact, I think there's Abell objects. I don't know whether he developed that catalog or they developed the catalog in his name. So, beautiful picture. Next slide. Oh. Another Brian Crawford beauty right there. I think I saw, tadpole. Aren't there also tadpole galaxies besides this nebula? I think that I've seen that term before. Nice shot, Brian. Brian, can you assure us that you're not tapping into the Hubble and stealing these pictures from?
Oh yeah,
He actually
the tadpole that was taken from my scope and Starfront, and then the Able 85 that was taken late last year from my backyard observatory.
Okay, we'll trust you on that. By the way, you might have seen in my article in the Guide Star in the February issue, there's a lot of nicknames out there which are used multiple times. Okay, but I don't want to digress here right now. Go ahead. Nice shot by Connor Kirkland. Another one on Discord. If you don't belong to Discord, Connor puts up a lot of nice pictures. And this one's Joey Rocco of M66. It's funny, just looking at this picture, looks like M66 has 2 galactic planes that are intersecting each other. That's just my impression. Again, throw in comments if you want to make a comment about these nice pictures. And who do we got now? John Stump, a budding astrophotographer with a horse head, and I forget what the thing to the left of the horse head is called.
I think it's the Flame Nebula.
Yeah.
Is the Running Man in there too?
Running Man's out of frame on that one.
Mm-hmm. Now, by the way, speaking of web, look at a web picture of the horse head sometime. It's amazing. Okay. Upcoming observations. Anybody see the February lunar occultation of Mercury? Any? At least put up a thumb or something that you did see it. We have members in other states who have clear skies, and they make us jealous by saying, "Oh yeah, I saw that." So, okay. Now don't laugh, but I'm going to say, did anybody see the March 3 lunar eclipse? So.
Yeah, it was eclipsed by the clouds.
And Venus-Saturn conjunction. I missed that one too. I'm going to talk about all planets lined up on the Wagman report, so we'll hold that for later. And I saw my first satellite and my first lightning bolt this year, so I'm a happy camper. Any other observations? Seeing none, I think that's it.
All right. Thank you, Eric. I appreciate it.
Mm-hmm.
All right. Let me just try to get back to my other presentation here. And then we shall move on. Okay. All right. Give me 2 seconds. I don't know why, like whenever you end one PowerPoint and you try to go to the other, I don't know why it just won't keep you connected and why you have to like reconnect again. It's kind of silly. All right. Okay, you should see my PowerPoint back up now.
No, I'm seeing, oh, there it is.
Oh, you see it now?
Mm-hmm.
Okay. All right, perfect. Okay, so officer reports. John, did you want to give any updates to everyone?
Yeah, so just in case you missed the very first couple of minutes of the meeting today, our speaker for tonight also lost power and was unable to present. And so she's going to be presenting on Betelgeuse and its theoretical companion star during the April meeting. The May meeting is still on track to be another Mars presentation on the Martian atmosphere. And then that's it for this season of our business meetings. And so if you're interested in giving a presentation, the next available slot is in September, and please reach out to me.
All right, sounds good. Thank you, John. Rich, did you have anything for recording secretary?
I think we lost him. Or he's muted. He's muted.
Okay, I'll circle back. Next on the list is corresponding secretary Lish. She messaged me and said that she was going to be out of the state, but she did not have anything to report. Next is membership secretary Gail. And I saw Patrick put in the comments that there wasn't anything to report. Treasurer Terry Mealy, I do not believe that he is on tonight. I know last meeting I talked a little bit about our last report. I do not believe I have received any updates from him that needed to be, talked about during this meeting. IT chairperson Michael Scovran, I do not believe that he is on. He has been communicating with us via Discord, sometimes email. He's still, continuing to do updates, monitor the website. There hasn't been any major issues to my knowledge, but if anything else comes up, I will let everybody know. Joyce, are you on tonight?
No, she's not. So she asked me to represent her. Just a quick comment about taking pictures at offsite star parties. And we could appreciate a few more from Mingo also. That helps promote future. If you show a picture from an offsite star party, that promotes people to come to the next one. And same thing with Mingo. That's it.
Okay, perfect. Thanks, Eric. All righty. So before we get to observatory reports, let's go ahead and welcome our new members. So we did have a few individual and family memberships that occurred in between our February and today's meeting. So here are the list of names of the individuals that have joined. Right now, with them as our newer additions, total membership is the 326, and last month I believe I reported there was 312. So to make it official, who would like to make a motion to accept these individuals that are displayed on the screen into our lovely club here in Pittsburgh? All right, I think Mary Devon, I see your hand went up. May I get a second? John Diller, his thumbs are going. All right, all those in favor, please say aye. Thumbs up. Aye. Are there any objections? Thumbs down or say no. Any abstains? All right, motion passes. Thank you very much, everybody. And welcome to our new members. Is there anybody that is new listed on tonight? I was trying to make a quick glance at the list to see if anybody stood out. So far, I'm not seeing anybody. So hopefully we'll get some more people joining in on our monthly meetings, because we're going to be coming into summer here pretty soon. Okay, moving on here. There we go. All right, observatory reports. Eric, you want to take it away for Wagman?
Yeah, sorry everybody to be hogging the mic tonight. I'll try to make this quick. As you may have seen in the guide star, we renamed what was the Manka telescope the Barban telescope. And now both observatory telescopes are named after accomplished telescope makers, John Bashir and Wade Barban. We went to his house to give him to his surprise, a plaque announcing the name change. I talked to his wife. It's hard to tell whether we can get him up to the observatory. He's in bad shape, but we may have him pay a visit. I was hoping he's here tonight. We could all give him a thumbs up. A couple quick other items. Scanlon roof was damaged, as you may have seen in the guide star, from not tonight's windstorm. I'm afraid to think what's going on tonight, but back in February, I think it was George Chase and Joe Mulqueen did a temporary repair, but we're definitely looking at a new roof at Wagner. The plan, I think, right now is to hold on to the existing roofs until next year so we don't run the club's budget dry. Dave Marcijanek says we're probably looking at 15 grand to put a new roof in, and if we do, there's better ways of adhering, attaching the shingles rather, so we'll be less susceptible to snow and wind. The Bashir end door, the little end doors at the end of the Bashir room. Jody Farr got up on the ladder and was actually able to pick the wood out with his fingernails. That's how rotted it was. So we're definitely looking at a carpentry repair job on that door. So what that means for the executive committee, I'm going to come hat in hand for more money. We're almost done with the renovations. We figured that the Scanlon door is okay for now. I'm proud to say we have a new couch at Wegman. You know their old saying, keeping up with the Joneses. Well, we're trying to keep up with Mingo. I always envied Mingo having a couch in the warm-up room. We had our first star party. Huh? Our first star party is not till 11. Here's what happened. We were up there doing some work of some kind, and people started showing up. And the phone started ringing. We want to see the alignment of the planets. And the news media, of course, distorted the whole thing, like you could look up at the sky and see this magical lineup of planets, and never pointed out that this is a heliocentric alignment, not a visual one that you see in the sky. So we had to disappoint people. I mean, Venus was up, I think Saturn, Jupiter, but they're spread all across the sky. So it makes our life tough when the news media distorts something that's happening. But anyway, we counted the people that came there as an unofficial star party. So that's everything I have. Mike Miller, any of the other Wagman committee members want to chime in on Wagman stuff that I might have forgotten?
Nothing in specific, although Jody did miraculously repair the Barbin telescope on the first night of it operating. The hand controller was acting up, and he found that if you push the switch over to the left, it makes the telescope move. So we're back in operation there. And I did use the Pi Finder on it on Monday, and it worked really good. The riggers were up there with me assisting.
Okay. Yeah, by the way, everybody, Mike Miller's doing a terrific job up there of repairs and upgrades. It's amazing the work he's doing. So
Thank you.
okay. That, unless there are any other Wagman committee members have any comments, that's it for the Wagman report.
Yeah, our new member, Michael Cartier, is the friend of mine that came up with me on the 6th to visit. He didn't tell me he was joining.
Yeah. Was that the night of the alignment?
Yeah, the alignment, air quotes. But there was like quite a few people up there. I think we said, what, 35, 40 visitors. It was, and people were very patient because it was a bit cloudy.
Yeah, and I took a couple of phone calls, and it was heartbreaking to disappoint them. But anyway. Okay, that's it, Kristen, for Wagman.
Alrighty. Brian, did you want to give an update real quick?
Sure. So tomorrow, Mingo is going to be holding its first committee meeting. We'll be having our director's performance review and vote of confidence. That's happening at noon. All 3 AP members are always welcome at our meetings. Just keep in mind that only committee members can vote. Following the committee meeting, starting at 1 o'clock, we will be hosting our first of hopefully many Mingo game days, game nights. So come on down, bring a board game, card game, puzzle, and come hang out in the clouds. We will be doing observing, weather permitting. It's not looking promising, which is typical during the good chance to perform a messier marathon. However, make sure you come down, hang out. We're all going to pitch in for pizza, order some pizza. We should have plenty of beverages there. One other note is as long as the locks will cooperate, which they should, hopefully, we will be changing our gate locks tomorrow. So now would be a good time if you like to visit Mingo. Make sure you can log into the 3AP website. That way you can get the new gate code. And of course, you can always message any of the associate directors or myself if you have any problems getting in. One other thing, not Mingo related, but NEAF related. Thank you everyone who submitted photos for this year's collaboration effort for the postcards. Those have been ordered and they are actually scheduled to arrive tomorrow. So thank you everyone. And any other NEAF update is just we've been planning and got a good team and everything's on schedule.
All right. Thank you, Brian. And for those of you that could hear like a little, howling going on in the background, that's our dog. Yeah. I kind of just put him in the bedroom because the dogs were just acting crazy because of the wind. So he's upset that he's locked away right now. I promise he's totally fine. So I apologize.
Oh, Kristen, one other Wagman item. If anybody is contacted by the Manka family about this name change, just have them contact me. I'll take care of them.
Okay. Yeah. So far, I haven't heard anything, but sounds good. I'll keep an eye out. All right. Were there any questions for the directors before I move on to the next slide or next item on the agenda here? Okay.
Test on Monday.
What was that, Eric? I'm sorry.
A test on Monday for what we said tonight.
Oh, I'm not grading it. That's all on you. All righty. All right. Old and new business. So for I guess I kind of combo because I really didn't have anything too new that we were going to need to talk about tonight. But basically, old business. Just circling back with the online store. Rich, I know you were. Oh, there. I see your mic finally turned back on. Do you have any updates about the store? Have you guys run into any problems or anything like that?
There was an initial problem or two with a couple orders. I ordered an embroidered polo shirt, and I needed to approve how the design would look before they would submit it. Laura ordered something that had a tariff issue. Anything that's come up that's an issue, we just took down from the site. A couple other orders went through no problem, so it seems to be working well with very little maintenance or monitoring needed by us. I check it every couple days just to make sure everything's processing well.
Okay. I'm sorry, Rich. I had a message come through from work. I'm kind of multitasking here. So just to recap what I believe you said. So just a couple issues here, but it seems to be working okay.
Yes.
Okay. All right. So I know we were giving this kind of a trial run with just the members. And I know we had discussed maybe potentially going public with the store. In your opinion, do you feel we're at that point, or do you think we need more time?
We only had about 4 orders come in. I mean, I think we're okay. I'll just have to keep an eye on it once we do go live.
Okay. Do you think we have like
live. We can go live.
Okay, I was going to say either that, or do you have a recommended date so that way you can, be able to monitor it? Like, obviously, volunteering. Like, I don't want to say, oh, we'll do it on this date if you're not, if it's going to be an inconvenience to kind of keep an eye on it.
No, just pull the trigger on it. Get it done.
Okay. All right. Are there any objections to that from the members? Like I said, I think we just made sure most of the quirks were kind of solvable. Like, is everybody okay with just going ahead and, letting the store go?
Yep.
Okay. All right.
By the way, fine job on all the people that pulled that together. Really nicely done.
Yeah, absolutely. Okay, Rich, if you we could probably let Heather panic, and I don't know if Lish had the link as well too, but maybe we'll just get in touch with them. And then were we putting the link on the website as well too, or was it just on Facebook?
We should put it on the website.
Yeah, that's what I'm wondering. I was going to say, go ahead.
I'm sorry. You see a lot of scams on Facebook of different vendors trying to sell name products from clubs and that. So I think the website would be better than Facebook, just to keep scams down. But either way.
Okay.
Can I just echo what I mentioned last month, that the current URL does look a little scammy, and it would be great if we had the ability to change that.
With the free site, we don't.
Okay.
Okay. All right. Okay, well then we'll just maybe we'll just let the IT committee know, and we'll let them kind of put everything together to make it go live, and then Rich just follow up and just let us know if there's anything else we need to do further with that.
Yep.
Okay, sounds good. All right. Again, NEAF 2026 is coming up. Brian did mention that plans are going well, and I think he said the postcards are going to be coming in tomorrow. At least that's what he told me when we were doing a brief before the meeting. Again, upcoming officer elections. So nomination committee chairperson. So far, I haven't had anybody message me or email me to say that they indefinitely want to do it. So just heads up, I'm probably gonna, be asking, some people I have in mind that could potentially be our chairperson. Again, this should be a fairly easy process since Rich introduced us to the ballot buddy, I think it's, or voter buddy, something like that. I'm sorry, Rich.
Election buddy.
What is it?
Election buddy.
That's it, election buddy. See, I was close. I knew it was buddies was in there. But regardless, so it should be a fairly easy process. We will have to, of course, accommodate, letter election ballots. We will have to, have the election also in person as well. So I believe for May, most likely we're going to be, I think we all decided we'll just like meet at Mingo, I believe is one of our past discussions, which makes sense because we would have the room to, have that event. So more to come on that. So the April meeting, that's whenever we're going to start, going over for the elections. So, okay. The first quarter executive meeting. So originally I did put out a meeting invite, but it turned out that because Mingo was planning on their observatory committee meeting around the same time, I thought that it would be wise just to wait until Mingo had their committee meeting. That way, if there was anything further that needed to be brought to the executive committee meeting, I wouldn't have to reschedule plan a secondary meeting. So we decided to go ahead and wait until after Mingo has their meeting tomorrow. So more to come, but obviously we are not forgetting to have this meeting, and I will keep everyone posted when that takes place. All right. So like I said, the old and new, technically I was kind of comboing it, like it is old business, but these are still, ongoing things. Is there, the next page is going to be going over the upcoming events for the club. So I know there was some things in the chat, so I am getting to that, but was there anything else that that needs to be brought up for new business? Like I said, that doesn't apply to like any events occurring this month and the next month.
Kristen, I just wanted to say that I received the library telescope that we won for Chartiers Houston Library. It came in from the Astronomical League. John and I are going to film a couple videos tomorrow afternoon with it, just to put on our YouTube channel, show how it works, how to use it, etc. And then we'll be presenting it to Chartiers Library later this month.
Okay, that sounds great. Thank you. And thank you, John, for volunteering to help with that as well, too. Okay. All right. And then, Britt, you know what? I just realized this. I don't think I put this on the slides. I saw you had somewhat of an update for the oh my gosh, the veterans. Did you need to talk about anything? I know, didn't you just recently go up there, I believe, right?
Yeah, I just went up there, when was it? Tuesday? Monday night I was up there. First time I'd been out there in almost 5 months. But it was a really good night. Everything was working fine. And we're going to just start back up. We have several volunteers who went through the process. George Chase is a volunteer for the VA. He's trained on it, so he can go up whenever he wants. Dan Den is going through the process. Brandon, I can't think of Brandon's last name, new member from last year. He's part of it. So we have a couple good volunteers, either training or trained. So hopefully we'll be able to use that a lot more this summer. We'll get out there for the vets a lot more.
Okay, sounds good. All right. Okay. All right, so event reminders. St. Patrick's Day Parade, I believe, is tomorrow. I know Patrick and Gail have been putting this together. They put out several messages on Discord. I believe there was the latest message was on. So if those of you who are on Discord, if you want to take a look, it's on the Non-Astronomy Get-Togethers channel on Discord. And there are directions on there as to where they are going to be meeting in Pittsburgh. I think when I read, it looked like they were going to be parking near the Harp and Fiddle. So for those of you that are familiar with that restaurant from Quaffing, that's where they're going to be at. So for those that have questions, reach out to Patrick or Gail. And like I said, there is details about it on Discord as well too. Next thing is the Astronomical League. I just wanted to put this out here since all of us now, we will get the event invites for this, but they are having a book club talk or seminar. I think I usually see their emails, but normally they do this like monthly. So the next one is scheduled for March 26th. It's going to be the book, I believe, is The Scheme of Heaven by Alexander Boxer. So just keep an eye out if it's something that you would like to attend. Normally they'll send out the meeting link a couple days prior to the meeting taking place. Again, observatory star parties for April 11th and 24th will be at Wagman. For those of you who would like to attend, or if you would like to volunteer to help out with the star party, please make sure you message the observatory staff and let them know. If you have questions, reach out. I know Eric and Mike and Jody, any of the Wagman staff, they are more than happy to give you information. Then on April 18th, there will be a Mingo Star Party that date. I do believe there was some talk about potentially having a combined event between the two observatories. I don't know if anything has been set in stone, if it was going to be like a members thing. Rich, I see your mic came off. Did you want to elaborate on that a little bit?
It's just in the discussion stage right now. We're talking about having the beginner telescope help, either a combined event, have it done at both observatories, same day, same time, or just one event at Wagman before their star party and one event at Mingo before our star party, just opening up early and inviting anyone who needs help with the telescope on to get help, basically.
Yeah. Yeah, I'm fine with that. I'm fine with that at Wagman as long as I can get somebody to do that training. I'm not the right person for that.
We'll have someone out there for it. But we're still debating on if it's 1 or 2 days, so
Right.
announcement to come.
Okay, that sounds good. I just remembered reading about something and it just kind of stuck out in the brain as I was going over everything. So thank you. All right, next, offsite North Allegheny. I'm sorry, I forgot to put the date down. It's actually, I believe April, was it 11th? I think it was a star party day as well too, when I saw it on the calendar. Let me pull it up real quick.
It is. It's April 11th. It's on it's not a 3AP event. It's, they
it's the
reached
20
out to us.
It's
Or is it the 24th?
yeah, I remembered it was a Friday. So yeah, it is the 24th. And I just had it marked at 8 p.m. So my apologies for that. But yeah, go ahead, Rich. I'm sorry.
Just North Allegheny School District. They do it every year. In the past, other members have helped out. I remember seeing it on our offsite schedule, and it kind of got pushed to the background a little bit, I guess. But they reached out this year through one of our members. I can't remember who. He was at the Cub Scout party, but they reached out, and we agreed to try to help them out if we can.
Okay. All right. So again, that's going to be on April 24th. And then the other event that's on the 11th is the Pittsburgh Photography Club show, which I believe, Rich, you were sending out emails. I think you said the deadline to submit pictures was yesterday, March 3rd. Was it March 12th? Yeah, I believe is what I saw in the Guide Star Express, correct?
Correct, but if you really wanted to, go ahead, get them to me in the next couple days and I'll squeeze them in. Just 2 maximum photos and they have to be deep space objects. And it's just a courtesy for the Pittsburgh Photography Club Salon. They're doing it since we've been doing the collaboration with them on the Astrophotography Star Party.
Hey, Rich, you had the delaying the photography club coming to Mingo. They were supposedly going to come on the 4th tomorrow.
It was going to be tomorrow.
And it's delayed till June. Do you know an exact date yet?
I can't remember what I gave them. I want to say the 12th. I can't remember, Eric. I got to look.
Yeah, let me know.
Yep.
All righty. Okay, and then last thing is I did see a message. I think it might have been through the Guide Star. John Diller, you were saying that the next quaffing event was going to be April 25th at, I'm sorry, is it Seeves? Is that how you pronounce it?
Yeah.
Okay, pub and restaurant.
Yeah.
Okay. All right. I don't think I saw what time. Was it 7 or was it earlier?
2 p.m.
Oh, 2 p.m. Okay, I'm sorry. I quickly went through that. All right, so just reach out to John if you would like to attend. Was there anything like specific, like do they have limited seating, or is it a pretty, sizable restaurant?
That's generally so I can have an idea when I call the place and how many people are coming, so they can prepare. It's not a case of getting reservations or anything like that, but they do like to know when there's a mass of people showing up.
Yeah, absolutely.
Like the one we just had at Boston too.
Mm-hmm. Yeah.
Okay. Yeah, and Patrick just made a comment and said they have a good amount of seating and parking at the restaurant. So, all right.
It is the old Prince Valiant Club for those of us of a certain age who remember ancient quaffing.
Okay. All righty. Okay. Was there anything else that needed to be discussed urgently tonight? No? All righty. Okay, I believe we pretty much covered everything. I know that I gotta jump off here pretty soon so I can get up to Pittsburgh, but I thank everybody so much for joining tonight amidst the strong winds. I hope everybody stays safe. I know there's a lot of debris on the road, and I've seen several reports of power lines, power poles coming down. So, if you are going out and about, just be very, very safe.
Yeah, where you work, Kristen, that's on top of a hill. You've got a lot of wind up there at Quest.
Yeah, actually, I've just been watching the news reports, and it's mostly the commute to get there that I'm seeing there's a lot of stuff on the road. So that's the part that makes me more nervous. Thankfully, I've been getting updates from work and our power is starting to come back on. So, again, that's another thing, of course, with like, being in a medical center, we want to make sure we get stuff going again. So hopefully by the time I get up there, all will be up and running. But sounds like they're doing a really good job getting things going again, which is great. It's mostly, the computers. That's the thing that don't always get on the backups on the generators. Alrighty. I think there was a message in the comments that I saw real quick. Rick, you were asking about who all is going to NEAF. If you want to reach out to Brian, Mingo director, he can give you a list of individuals that are going up there. And they can also give you some contact information if any members are going up to NEAF, if they want to, swing by the booth, or if they just want to, see if they can grab like a meal with, with everybody as a group, coming from Pittsburgh. They can give you some contact information. Alrighty. So can I get a motion to adjourn the meeting for tonight? I saw Joe's hand go up. Joe, I apologize. I don't know what your last name is. I'm going to look it up right now. Let me see here. Oh, I actually don't see your last name on the thing. I don't know if you can.
So Joe Malqueen.
Oh, okay. Thank you. I didn't know which Joe it was. I was like, who? All right. May I get a second, please? Rich?
So moved.
Oh, or John. I think Rich got his hand up first, John. All right. All those in favor say aye. Thumbs up.
Aye.
Aye. Thanks again to John Wenskevich for coming through in the pinch.
Yes.
That was a lot of good
Amen.
information there. For someone who has researched this a lot, there was a lot of things I learned tonight.
Yeah.
All right. Are there any abstains? Or not abstain? I'm sorry. Any objections? Sorry, I jumped the gun. Okay. Any abstains? All right. Motion passes. Thank you very much, everybody. And yes, again, thank you, John, for the presentation on such short notice. I'm glad you have those PowerPoints stuffed away somewhere for emergencies.
Yeah, there's still a few more just in case, but definitely we would rather have other people speaking.
Absolutely. All right, everybody. I'm going to